In this episode of Mr. Lehman's Knowledge Explosion, we're going to discover how to use congruent triangles to make theorems and statements about specific objects such as isosceles triangles. So let's start by reviewing what a congruent statement means. A congruent statement, much like the one I gave you here in the corner, like triangle ABC is congruent to triangle XYZ, should tell us the 6 congruent parts of the two triangles. For example, I know that since A is the first letter, angle A is congruent to angle X, the first letter in the next triangle. Likewise, angle B is congruent to angle Y, and angle C is congruent to angle Z. So just based on the congruent statement, I should be able to go back to my triangles and mark, yes, A is the same as X, angle B is the same as angle Y, and angle C is the same as angle Z. So that way, even if the triangle gets rotated or flipped, such as this example, I can still match up the correct parts based on my congruent statement. We can do the same thing with sides. AB is the first 2 letters, so that would be congruent to side XY. BC are the second and third letters, so that would be congruent to side, I'm sorry, not X, but YZ. And then the last one, A and C, should be congruent to segment XZ. And again, I could go back to my triangles and I could mark that. AB is the same as XY, and BC is the same as YZ, and AC is the same as XZ. Now, even though it may not look like it, we go by the congruent statement, and that way if it's rotated or flipped in a way we can't see, we still know. Now that whole idea boils down to this one statement. Corresponding parts of congruent triangles are congruent. We're going to abbreviate that CPCTC. So this is used after we prove 2 triangles are congruent. And it simply says that all those parts we just marked are the same. So we use it after we prove triangles congruent. Only after. Okay, so it always follows a congruency statement. So let's look at an example of a proof and see how we can make this work. In this proof, we are told that FL is parallel to WH, so I'll start by marking that. And we're also given that side FY is congruent to side WY. So I start with my given information, and it says prove, so I'm going to mark this in a different color because we don't know this yet. It says prove to me that FL, this side over here, is in fact congruent to HW over here. So our goal is to show that those 2 red things are congruent. Well, the simplest way to do this is to say that the 2 triangles are congruent, and then say, well, that means all the sides are the same by CPCTC. So let's take that off there so we don't confuse it as something we actually know. So I'm looking at the picture and I notice that I have a pair of vertical angles, angle FYL and HYW, that I could say are congruent. So I'm going to say angle FYL is congruent to angle HYW because vertical angles are always congruent. And I mark that in my picture so I can see it. So right now, if I just jot down what I have one set of sides and a set of angles. So I'm going to look for another set of sides or angles. Parallel lines is a big clue. Parallel lines always give me things like corresponding angles or alternate interior. So I'm going to look for those. And what I notice is angle H and angle L are alternate interior. And if you don't see that, draw the parallel, and the transversal that creates angle L and angle H. And since there's only one angle L or angle H in the picture, in my proof I can simply say angle L is congruent to angle H because if lines are parallel, then my alternate interior angles are congruent. So now when I look back at my picture at what I have marked, I have not just one set of sides and one set of angles, I have two sets of angles, and I want to see the relationship that they have. If I look at this, it appears that I have an angle followed by an angle followed by a side that matches an angle followed by an angle followed by a side. So what I'm seeing in my proof is that my triangles are in fact congruent. So statement number 4 is not going to be angle, angle, side. It's going to be that my triangles, FLY and triangle WHY, are congruent because of the angle-angle side relationship that I have. And when you're writing that, you want to be careful. I do need to make sure my congruent statement is correct. Angle F does match angle W, L matches H, and Y matches Y. But that just tells me the triangle is congruent. So we're going to finish this proof, statement number 5, by saying, well, if the triangles are congruent, then that side FL has to be congruent to side WH because of what we did at the top. All 6 parts are going to match. And the reason we use to abbreviate that is corresponding parts of congruent triangles are congruent, which we write as CPCTC. And we've proven that those two sides are the same. That's how we're going to use this idea in our proofs. So let's turn the page and look at how I can prove something specific about an isosceles triangle. Now what you have to understand about an isosceles triangle, from the definition, we know that two sides are going to be the same. So if the vertex angle is angle G, I know that sides GF and GH are going to be the same. What we're going to try and prove is that just by knowing that, somehow angle F and angle H also have to be the same. Well, you might be asking yourself, how am I going to use congruent triangles when I only have one? Well, that's where this idea of an auxiliary line comes in. If I draw a segment from the top to the bottom, I can use that line to separate the isosceles triangle into two triangles. But what I'm going to do is draw it in such a way that I am purposely drawing it to the midpoint of HF. So I've constructed that line to the midpoint. So my proof is going to start with simply the given information. I was given isosceles triangle GFH. That was it. But then I have to let people know where that midpoint came from. So I'm saying that, let's call it point M. M is the midpoint of segment FH. Now your reason for that is you drew that, or I drew that in there, so we're simply going to say I constructed that line, or by construction. Now we can use that. I have two triangles and I have some information about those triangles. I'm going to try and prove them congruent so that I can say the two angles F and H are the same by CPCTC. So in statement number 3, I'm going to take that idea of midpoint and continue on with it. If M is the midpoint, that means FM has to be congruent to HM because that's what a midpoint is, or the definition of midpoint. So I'll mark that on my triangle. FM is the same as HM. And hopefully some of you are already seeing I've got two sets of sides that are congruent, but because that segment I constructed straight down is used to make both triangles, it has to be congruent to itself by the reflexive property, giving me a side-side-side relationship for those two triangles. So those two triangles, when I draw to the midpoint, have to be the same, but I do need to mention that in my proof. I have to say that segment GM is congruent to segment GM because of the reflexive property. And now I have three sets of sides that are the same, so I can say in statement number 5 that my triangles GFM and triangle GHM are in fact congruent by a side-side-side relationship. But if the triangles are congruent, that means that all the pieces are the same. And what I was trying to do at the beginning was convince people that angle F and angle H do in fact have to be the same. Well, they have to be the same if my triangles are congruent, or corresponding parts of congruent triangles are also congruent. So there's my proof that in every isosceles triangle, the angles across from the two sides that are congruent are also the same. So let's look at an example on how we can use that. If two sides of a triangle are congruent, then the angles opposite those two sides are also congruent. That means if I start with an isosceles triangle, and here like in example number 1, this angle across from that side and this angle across from the congruent side should be the same. So I can mark that. This angle and this angle are the same, which means angle X is 65 because the triangle is isosceles. And now that I know two of the angles in the triangle, 65 plus 65 is 130 degrees, since I only get 180 degrees total in the triangle, if I subtract that, that leaves me 50 degrees for the vertex angle Y. But what about the next example? It's not limited to only two sides. Any two sides in a triangle are congruent, then the angles across from them are the same. So I like to draw these arrows. Since this side is congruent to this side, that means angle X equals angle Z. But this side is also equal to those two sides. Oh, I just realized this is supposed to be a Y up here. Sorry about that. Those two sides are also going to equal the other angle there. So all three of these sides are the same, which means all three of the angles across from those sides are the same. And since I only get 180 degrees in a triangle, split evenly three ways means each of those angles is 60. So think about what we started with. We started with three sides the same, which means our triangle was equilateral. But we figured out that since those sides are the same, it means the angles are the same. We proved or showed that it's also equiangular and all those angles are 60. So if you flip the page, there's a theorem that we say. We say if a triangle is equilateral, it's also equiangular. And we can use that to know the measures of every equilateral triangle ever. Now in the next video, we're going to prove the converse of the isosceles triangle theorem to see if that also is true.